You can think of verification validation as a formal process for checking results. It's extremely important in practice. Here we'll do it in a quick and dirty way just to keep things short, but also get you in the practice of undertaking this. And as I've talked elsewhere, these terms have verification, validation, they have separate meanings. And quickly, verification is whatever mathematical model I picked, did I solve it accurately enough? So it's looking at this branch, whereas validation is looking at this branch, i.e. whatever mathematical model I picked, is that even accurate in a representation of the physical problem? And validation involves experimental data, which we don't really have here. So we won't do validation and we'll do verification. And verification builds nicely on the pre-analysis steps. So each step of pre-analysis has a corresponding verification step. We looked at what the mathematical model was, and so in verification, we can check if our results are consistent with that mathematical model. We looked at what the numerical solution procedure and the associated numerical errors are. That's looking at this aspect, and the corresponding thing, to do in verification is, are the numerical errors acceptable? And then we did hand calculations of expected results, and so we can check if our results compare reasonably well with hand calculations. And we've been doing that a little bit along the way. And if you look at this list, you can come up with a nice checklist that is actually pretty much independent of the kind of analysis you're doing. So it's quite general. So if you look at the first aspect, are the results consistent with the mathematical model? Boundary conditions is where people trip up a lot. So you can check your boundary conditions. We did for displacements, which is very easy to do. The stresses are a little bit more involved, and I will leave that to you. And you will see that the stresses, because they are essential, they are natural boundary conditions, won't be satisfied exactly, but they'll be satisfied reasonably well, and the agreement will get better as you refine the mesh. Check material properties. I threw that in there because this is someplace, this is one place where people often trip up. And so you can check if you put in the right material properties into the mathematical model, and then we can check equilibrium in aggregate, because the basic physical principle on which the governing equations are based is equilibrium of an infinitesimal element. Now, since we have an approximate solution, it won't satisfy equilibrium of an infinitesimal element or even a finite element. But it will satisfy equilibrium in aggregate. And this doesn't mean, if equilibrium is satisfied in aggregate, it doesn't mean that your stresses are accurate. It just means that, you have, it's kind of a necessary condition to be satisfied to make sure that everything is self-consistent after you do the discretization. And the second aspect, are the numerical errors acceptable? We saw that ANSYS by default is already using a higher order polynomial, and the numerical errors come from the polynomial interpolation. So all we need to do here is check the discretization error by refining the mesh. And then the third aspect is checking against hand calculations. And in fact, that is also in, really checking consistency with the mathematical model, because the mathematical model used in the hand calculation is almost the same as the one in the FEA. So I will just give you a quick overview of that, checking equilibrium in aggregate and refining the mesh. So if I go to the model, okay, now ANSYS has the stresses at all the surfaces, and they can be integrated to find the resultant forces. And so we can get it to do that. And in fact, there is a shortcut for that. You can just take your, the displacement boundary condition and drag it to solution. And you'll see that it adds a force reaction. And in fact, it'll give you the force reaction over here. And so I'll say evaluate all results. And if I expand results here, it says, oh, over the x-axis, it's 10 to the power of minus 5, y-axis. So in the x and y directions, the resultant force on this surface is almost 0, whereas, and then also in the Z. So there are no resultant forces on the surface, and that's what we expect. We can also look at the moment reaction. For that, you highlight solution in the tree and you say insert probe moment reaction. You can also do it over here, and you can do this for any displacement boundary condition. So essentially where you specify the displacements, now ANSYS calculates the stresses, and then from the stresses it calculates the equivalent moment, similar to what it does for the force reaction. And here you see that the moment in the X and Y are small, and the Z should be opposite to the applied moment, and that's indeed the case. So equilibrium is satisfied in aggregate, and then if you want to check the discretization error, you can refine the mesh by going in and changing the phase sizing. You can make that, half of this, maybe 0.35, and then you can have more elements with thickness, and for that you would go into mesh, sizing, you would go under capture proximity, and then change, increase the number of cells across gap to say 5. And then check how much your results change. I'll let you do that. So that brings us to the end of this tutorial. And I've learned a lot from this problem, and hopefully that's been the case for you too. And make sure you save your project, and also you save your files.